Let's now formally define what an asymptotic upper bound is. Typically, we have to consider two functions in order for us to really give the definition. So we got two functions over here. We got f of n, and also we got g of n. And notice that for the domain of the two functions, they are both positive integers, and they actually denote the sizes of input. So meaning that it can be 0, can be 1. Well, 0 is strictly speaking is not really a positive number, but you can assume that the input size should be at least 1. So it can be 1, can be 2, can be 3, but just cannot be negative. So that'll be the domain, the input for the function n over here, right? For both f and g. What about the output for the function? So the output for the function will be positive real numbers. So they will denote the running time. You can think about the running time over here, maybe the more like a physical running time, the absolute running time. So now we are talking about math. We're not talking about the relative running time just yet. So for now, just focus on the formal definition for these two functions. So there'll be positive real numbers, and then what about f of n? So f of n, by convention, is going to characterize the running time of some candidate algorithm. You can think about this as the algorithm that we want to consider for its performance, maybe against the running time of another algorithm. What about g of n? So g of n may be the most maybe the usual confusing point when you first learn about the notation. Let's see. So g of n, you want to really understand this notation very well. Okay, so g of n is over here, and this is the so-called big O notation, which will give its formal definition in just a moment. Okay, so we'll say big O, and then with opening parenthesis, enclose it with another matching closing parenthesis. So we say this is the big O of g of n. Okay, again, it's called the big O of g of n. So what does this really denote? Okay, let's now go over that. First of all, when I say big O of g of n, I'm not talking about just a single function. It basically denotes a collection, a family of functions. Okay, number one. And number two, what does the family really contain? What are the members in the function, in the family? Okay, it consists of all the functions that can be upper bounded by g of n. So the words over here, I didn't really highlight it, but upper bounded here is really the key word. But I will show you exactly, mathematically speaking, what do I really mean by upper bounded. Strictly speaking, it's just a less than or equal to relation. Okay, it's going to be upper bounded by g of n. So g of n, all the functions that can be upper bounded by g of n by some I'll get to that in a moment. All the functions that can be upper bounded by g of n is called the big O of g of n. So that's how you interpret that informally. But how do we find out the upper bound effects? You have to find two things. Number one is, where does it start for the upper bound effects? It should start at some points. It should start at some point of the value for n. And usually we denote that as n0. And also, in order to really have the upper bound, you have to multiply g of n by some multiplicative constant or constant factor, some constant. Okay, so these are the two things. Let me recap very quickly. You should really know about two functions over here, f of n, which is the algorithm that under consideration, and also g of n. G of n is more like a reference point. Itself may or may not upper bound f of n. It may or may not. However, we want to say the big O of g of n. So the big O of g of n is simply a family of functions. First of all, it's a collection of functions, not just a single one. And also, what does the family really represent? It represents all the functions that can be upper bounded by multiplying certain multiplicative constant to g of n. And also, the input value starting at some point is going to have the upper bound effects. That's basically the definition, informally. Let's now define that formally. Well, let's say here, for those of you who may have learned about some set theory, so this symbol over here simply means a member of, right? Remember I said before, this is a collection over here, so you can think about it's like a set of functions. And we are saying that the algorithm, the running time of the algorithm under consideration is simply f of n, and that should be a member of that. This will be the case if these two witnesses can be found. the witness number 1 is a real constant c larger than 0. You can think about the c over here is about the constant factor that we spoke about, number 1. And also there should be another integer constant n0, right? I spoke about n0. It is the starting point, right? So we said starting at some point. So this will be n0 larger than or equal to 1. Remember we said before the input domain for f and g should be positive integer. So that's why we say larger than or equal to 1. We don't really consider input value being 0. All right, so far so good. And here is the very simple relation to really characterize the upper bound effects. You can see f of n is upper bounded by not just g of n alone. Rather, it's going to be upper bounded by a multiplicative constant c that we have chosen. And then this upper bound effect is going to happen for n larger than or equal to n0. Over here, that's a starting point. Okay, it's a little bit dry just by going over the definition, but at least I want you to see all the ingredients for the definition, and then we'll do examples. So don't worry. All right, let's now learn about some terminology, like a pronunciation, or how you should really learn about the vocabulary whenever you want to talk about big O. So for each member function f of n in the big O of g of n, right? We say that you can either say f of n is a member of big O of g of n. So that's something we just said. If you consider big O notation is a family of functions, okay? Or alternatively, you can also sometimes people also say f of n is big O of g of n. That's might be something you hear the most common. Okay, well, I would say that very often as well. Okay, so but you should really notice that it is over here, mathematically speaking, is really a member of, not just saying that a single function is a single function. That's not right, precisely, right? Precisely speaking, so this is a family, like a collection of functions. All right, finally, this is maybe slightly less common. You can also say f of n is order of g of n. In that case, you don't really say the big O, right? That's just another alternative. So you want to make sure you understand the different ways of saying the same thing. All right, so that's about the definition for big O of n. The big O notation. Okay, make sure you review the formal definition whenever you need to. But I think as you apply more and more examples, you should be able to somehow memorize by heart and also by understanding. Let's see one example right away. Okay. Oh, before that, let's we will see example, and also we'll try to visualize what's happening over here. So this is some diagram to actually show you the upper bound effect. Let's now switch to iPads over here. Okay, this is the formal definition I just mentioned before, and just to really remind you, this part over here is the upper bound effects. And in order to really prove the upper bound effects, you are supposed to find, in order to prove the upper bound effects, you need to find the multiplicative constant c and also n0 over here. So these are the two things you need to find in order to prove it. Okay. Okay, so these two need to be found, need to be identified in order to prove that f of n is actually a member of big O of g of n. Right? So these two numbers are actually what you're supposed to find in order to prove it. Right? We'll see example for sure. But let's look at this diagram over here. I simply got this diagram from some textbook. It's pretty good, but it's not complete. I will have another complete picture to show you using the example, but it's good enough. So this is a starting point, n0, that we are supposed to find, and also the c over here is the multiplicative constant, right? So now what you can see is over here, f of n over here, what you should really see is this point over here, at this point. Before n0, strictly less than n0. When the input size n is strictly less than n0. As you can see over here, this is f of n, right? Is it upper bounded by g of m, the blue one? It is not. It's the opposite, right? So here, it is not. It is not the case that f of n is actually less than or equal to c times g of n, right? It's simply not the case, because you can see g over c times g of n is actually strictly less than f of n. So the upper bound effect is not really occurring before n0. That's why you are supposed to identify the starting point. Okay, and then symmetrically, so now I can draw something over here. Let's say here. So starting from n0 over here and onwards over here, right? Basically. So here, when n larger than or equal to n0, it is the case that f of n is less than or equal to multiplicative constant c multiplied by g of n, right? It is the case. It's really important for you to see that. Right? You can see f of n, which is over here. For every input size over here, the corresponding running time over here is actually less than or equal to the corresponding input value for c times g of n, right? So this is where the upper bound effects actually will be effective. Okay, let's now consider one example, right? And then I'll come back to the illustration point. All right, let's now consider this function here. Let's say 8n plus 5. You can think about 8n plus 5 is similar to kind of similar to the find max primitive operation number that we came up with, right? But just a different example. I want to prove that 8n plus 5 is a member of the family of functions of n over here, the linear function, right? So well, alternatively, we can say 8n plus 5 is big O of n, right? Remember the different ways of saying the same thing. How do we prove it? All right, and based on what we said so far, it should be ready to actually prove it by using the definition and using the visualization I just illustrated to you. I would suggest you pause the video and then try to do a sketch of the proof and then resume the video. All right, assuming that you thought about it, let me give you a little bit more hints in case you actually got struggle. And after the hints, you can feel free to pause the video again just to make sure you can really do it from scratch by yourself. The strategy will be you have to choose the real constant c larger than 0. So this will be the multiplicative constant, right? Eventually. And so you can think about this is the g of n, and this is the f of n. That correspond to our definition. And then you want to find out what n0 is. And then you want to make sure once you find out the n0, you want to say starting from n0, it is the case that an plus 5 is upper bounded by c times n, right? Exactly what we said before. Let's now try to, since it's your first example, you can definitely feel free to pause the video and think about what c should be and also what n0 should be. I can tell you that the solution may not be unique, meaning that there might be different ways actually for you to actually prove it by choosing different pairs of c and also n0. But I will just give you one possible solution. And then later I'm going to give you a proposition of the big O, meaning that you can always choose a winning witnesses without thinking too much. Okay, that will be the flow. All right, you can pause the video and think about what n0 should be and what 0 should be. Assuming that you thought about it, let's now see. Okay, can we choose maybe 9, for example? Right? For example, just asking. So maybe that's what you chose. Maybe it's not. But let's say we choose 9. Let's say we choose the multiplicative constant c here. Then intuitively, since this is 8, right? So why don't I simply choose something that's strictly just larger than that, which would be 9, right? In that case, that's not complete because I also need to choose n0. I need to show that at some point, an plus 5 will be upper bounded by 9 times n. That's something I need to show, right? Before I show you that visually, why don't we use something that that's actually more naive, and then just use a table to actually enumerate all the different values as the input size grow. Why don't we try that? Okay, so this is a table. So this will be input size starting from 1, right? It must be positive. And also that's the algorithm running time, f of n. And this will be, n itself is the g of n. And 9 is the multiplicative constant that we have chosen, right? You gotta be very clear about what each component is, okay? So now, in the case where n is equal to 1, plug it in, you got 13, right? Hopefully I don't need to explain why. And then that will be 9, right? Does the upper bound effect happen just yet? No, because 13 less than or equal to 9 is not true, right? We need to see this over here is less than or equal to this over here, right? But it's not happened just yet. What about n is equal to 2? In that case, this will be 21 less than or equal to 18. Not true, okay? What about 3? 29 less than or equal to 27. That's also not true, but we're getting closer, okay? What about 4? 37 less than or equal to 36. That's also not true. So we haven't found n0 just yet, but we are approaching, hopefully very soon. 5 seems to be very promising because you can see after plugging 5 into this function here, we got 45, which is equal to 5 plug into 9n, which will be 45 as well. It seems like the upper bound effects less than or equal to is start to happen, but we want to be a little bit more conservative. You want to just try a few numbers just to make sure the trend is not going to negate the upper bound effects. What about 6? In the case of 6, it will be 53. Definitely is less than or equal to 54, the corresponding number. So you can definitely feel free to try out a little bit more numbers, maybe up to 10, just to make sure the upper bound effect is always there. And then you can safely assume it's gonna actually going to maintain for the upper bound effects. Okay. So what we have done so far is we have chosen c to be 9 over here, and also n0 to be 5. Starting from which we got upper bound effects, right? And that's actually how we prove it. And one question for you. We may also prove it by choosing a larger multiplicative constant, 13, as opposed to 9. And then, in that case, intuitively, since the multiplicative constant for n is actually larger, right? So which means this part here is actually larger, right? In that case, intuitively, we can expect that the starting point for the upper bound effect can occur sooner. It will occur sooner at 1 rather than 5, right? So hopefully you can see that. That's why I'm trying to give you the alternative. If you want the upper bound effects to actually occur sooner, in that case, you want to actually choose a larger multiplicative constant. Remember this insight over here, because when we actually show you the proposition of always choosing the right witnesses for C and also n0, this is something that we'll actually end up having. Okay, just remember. But for now, as far as this slide is concerned, you just need to remember. You just need to understand why this proof will be valid, and also this proof will also be valid. That's the main point. Okay, let me conclude this example by showing you one more visualization. Okay. All right. So here, okay, let me just go back here. Okay, good. Right, so if you go back to the notes, what about n0 when you choose actually 9? So that'll be 5. Okay, that's something we already spoke about in detail using the table. And now I just want to give you one more illustration over here by using this particular example, right? Let's now use this diagram to recap what we have learned so far about terminology. Okay, so first of all, we got f of n over here. Okay, let me make it a little bit thicker. F of n, and this is typically the running time function of some algorithm under consideration. Okay, let's do one at a time. And then this part over here is the, let's talk about g of n over here. G of n is simply just n. So that is actually a linear function, okay, over here. So n over here is the, you can think about this is a reference function. reference function, we aim at proving that the f of n over here, f of n is actually a member of let's say the big O of g of n over here. And in order to do that, what should we do? Well, what we should do is we should really accordingly, what we should do is we should really choose C and N0 such that, well, remember the formula. So since I've done this for many times, so that's why I have already memorized it. But for you, you're still learning. That's okay. But try to catch up with me. So what we can have is, you want to say you got the upper bound effects over here, right? Less than or equal to. In that case, first of all, we're going to put f of n is going to be upper bounded by some multiplicative constant. Let's say it's going to be something that we have chosen, which will be c, and then it's going to multiply by, so multiply by g of n, right? And when does this upper bound effects occur? There's got to be a starting point for n, the input size, larger than or equal to the n0 that we have chosen, right? So that's the story. Okay. And one thing to note over here, which I didn't really say in the earlier diagram. You can see in the earlier diagram over here, we only show you c multiplied by g of n already. We didn't really show the g of n itself, but in this diagram here is actually more valuable because we are showing that to you. Okay. Now I want you to consider g of n, which is over here, right? It's a linear function, right? So this is g of n, and this is f of n. Can g of n itself upper bounds f of n? Let me put it another way. Can f of n ever be upper bounded by g of n at any points? It's simply not possible, right? It's a very important insight, first of all, to actually say. Okay, so let me say that. Let me use orange over here. So you can see over here, and also over here, I want you to focus on these two lines over here, right? If you look at these two, you can see g of n can never be f of n can never. Okay, how about this? Let me put it this way: can not be upper bounded by g of n at any point. And let's be a little bit more precise. F of n less than or equal to g of n is not true for any value of n. All right, so this is why choosing the multiplicative constant c over here is so important, right? Let's now complete the puzzle over here. Okay, you can see once now I want you to consider this line over here and this line over here, right? These two lines, right? So these two lines are closely related in the following sense. This line over here is g of n, and by multiplying it by some multiplicative constant that we have chosen, we will be able to increase the slope of the line so that we will be able to actually upper bounds f of n. That's really the important point to notice. Okay, so let me write it down. So the line over here is really the c. Okay, after we actually have done this, so this actually is visually speaking increases the slope of g of n, right? So after that, so now finally you can see if you actually consider these two lines over here, if you consider this line over here and also this line over here, f of n, I'm just using a slightly different color here. So now if you look at this one here and this one over here, we are basically talking about the same diagram over here. The multiplied G of n and also f of n. We can definitely upper bound f of n by using this starting at some point, right? Let me just say one more thing and then we are done, right? Hopefully it's not really too complicated. I just try to really explain every bits, just make sure you're okay with the definition. Okay, so finally I'm just going to look at these two lines over here, this line over here and also this line over here. So starting at this point over here, okay, so here when n is actually larger than or equal to n0, and in this case is simply equal to 5, right? So remember the 5 that we found before. So this is the n0. F of n is actually less than or equal to the multiplicative constant c, which is 9, multiplied by g of n. Right? Only after this point you can actually see the you can see the effects over here, basically like that, right? Only at this point. But before that is the reversed over here, right? Before that, which we spoke about earlier. All right, I'm not gonna annotate any further, otherwise it'll be too messy for you to really study later. All right, let's now move back to this example here. All right, so we got one more example for you to practice. So let's say this, we got f of n over here again. It's slightly more complicated function over here. I want to prove that this f of n is big O of n to the power of 4. Well, I can say f of n is the order of n to the power of 4, right? Or I can say f of n is a member of the big O of n to the power of 4. Either way, right? I already showed to you 3 different ways of saying the same thing. And you can definitely complete this exercise on your own. I'm going to rely on you. It's going to be done in a very similar way. And I will also encourage you to really try to plot some graph like this to really see all the 3 functions over here. F of n, g of n, and also g of n multiplied by the constant factor. And to see where this upper bound effects will actually start. I will highly encourage you to really do this just to make sure you understand the basics completely. Right? You can definitely see the solution over here, but I'll let you actually justify yourself, to check yourself to make sure that's the proof actually makes sense to you. All right, and before we actually see more examples about the big O, I would like to talk about 2 propositions or properties of the big O notation.